AI accelerators are revolutionizing how we handle complex AI workloads today. Traditional GPUs have been the backbone of AI processing for years. However, AI model complexity is rapidly increasing. Emerging accelerators like NPUs and TPUs are tailored for AI tasks. AI models like GPT-3 require 175 billion parameters, challenging hardware limits. This complexity pushes traditional hardware beyond its capabilities. NPUs are designed specifically to accelerate neural network computations. TPUs, developed by Google, excel at handling tensor operations. AI accelerators offer significant performance gains over traditional GPUs. AI accelerators are crucial as AI models grow more complex. The future of AI hardware is being reshaped by these accelerators. In conclusion, AI accelerators are crucial for advancing AI capabilities. Graphics processing units, or GPUs, are the traditional powerhouse of parallel processing. GPUs are designed to handle thousands of simultaneous threads for massive parallel tasks. This architecture makes GPUs ideal for tasks like rendering and deep learning. NVIDIA's A100 model boasts 40 gigabytes of VRAM and 19.5 teraflops of performance. GPUs have been crucial in training large language models over the past decade. Parallel processing allows GPUs to handle complex computations efficiently. Their architecture excels in tasks that can be broken down into smaller parallel jobs. GPU's ability to handle data in parallel increases processing speed significantly. Their versatility has made GPUs popular in both gaming and scientific research. Despite their power, GPUs are energy-intensive and can be costly. The market for GPUs continues to grow, fueled by demand in AI and gaming. As technology advances, GPUs remain a key component in cutting-edge applications. GPUs will continue to evolve, adapting to new challenges and opportunities. NPUs are specialized processors designed for efficient neural network computations. Unlike general-purpose GPUs, NPUs focus solely on neural network tasks. Huawei's Ascend 310 is an example of a powerful NPU model. It can achieve up to 16 teraflops of processing power. With 8 gigabytes of HBM, it handles large data volumes efficiently. NPUs are more energy efficient than traditional GPUs. This specialization reduces energy consumption during intensive computations. The architecture of NPUs is tailored for deep learning algorithms. NPUs can execute operations like matrix multiplication more efficiently. Their design allows for parallel processing, maximizing throughput. This focus on efficiency makes NPUs ideal for mobile and embedded devices. As AI demands grow, NPUs will play a crucial role in future technologies. Their unique capabilities set them apart in the AI accelerator landscape. Google's TPUs revolutionize tensor operations, crucial for AI workload efficiency. TPUs are designed specifically for tensor operations, unlike traditional processors. TPU v4 offers up to 275 teraflops performance for high-intensity AI tasks. This performance surpasses many modern GPUs in AI-specific tasks. TPUs are cost-efficient in terms of power consumption and performance per dollar. Google's TPU architecture is tailored for deep learning models. TPUs excel in training large neural networks quickly. Compared to GPUs, TPUs offer superior performance in matrix operations. TPUs are integrated into Google's cloud services for scalable AI solutions. The scalability of TPUs supports vast AI workloads efficiently. Google's TPUs continue to evolve, pushing AI boundaries further. Looking ahead, TPUs promise to enhance AI capabilities even more. FPGAs, or Field Programmable Gate Arrays, offer remarkable flexibility for AI workloads. ASICs, or Application-Specific Integrated Circuits, are tailored for specific tasks. The Intel Stratix 10 FPGA is known for its adaptability in AI applications. Xilinx's AI engine enhances performance through specialized processing capabilities. FPGAs are highly effective in edge computing environments. ASICs provide unmatched efficiency for repetitive tasks in AI. FPGAs can be reprogrammed for different tasks, offering versatility. ASICs are ideal for large-scale AI deployments. FPGAs balance performance with power consumption effectively. Edge computing benefits from FPGAs' adaptability and low latency. ASICs excel in environments where power efficiency is crucial. Choosing between FPGAs and ASICs depends on specific application needs. Both FPGAs and ASICs push the boundaries of AI hardware innovation. Let's compare the performance of GPUs, NPUs, TPUs, and other accelerators. GPUs are known for their high teraflop performance, often exceeding 20 teraflops. NPUs focus on optimizing neural network tasks with efficient power usage. TPUs are designed for tensor operations, excel in AI tasks like training models. In energy efficiency, NPUs lead with only 5 watts per teraflop. Cost effectiveness of accelerators varies widely based on use case and scale. MLPerf benchmarks show TPUs outperforming GPUs in training time. Real-world examples highlight the cost savings of using TPUs for large-scale AI. FPGAs offer flexibility, but often at the cost of lower raw performance. ASICs are custom-built for specific tasks, offering unmatched efficiency. Let's look at a terminal command output from an MLPerf benchmark test. In conclusion, choosing the right accelerator depends on your specific AI needs. The AI accelerator market is projected to reach $83.25 billion by 2027. Autonomous vehicles are at the forefront of adopting AI accelerators. Cloud computing services are rapidly integrating AI accelerators too. The adoption rate is increasing across multiple industries. Healthcare is also a significant adopter of AI accelerators. AI accelerators enhance data processing speed and efficiency. Financial services leverage AI accelerators for real-time analytics. AI accelerators are pivotal in advancing machine learning models. The gaming industry utilizes AI accelerators for enhanced graphics. AI accelerators are essential for real-time decision-making in robotics. The adoption of AI accelerators is expected to continue growing. AI accelerators drive innovation across diverse sectors. Key industries are investing heavily in AI accelerator technology. AI accelerator adoption is reshaping business strategies globally. The future of AI accelerators promises even greater market integration. AI accelerators face challenges in software compatibility across different platforms. Development costs for AI accelerators remain a significant barrier for many companies. The learning curve for new hardware can slow down its adoption. Quantum computing breakthroughs may redefine AI accelerator technologies in the future. Quantum computing could significantly disrupt existing AI accelerator markets. Current AI accelerators are optimized for specific tasks, limiting their versatility. Integration with existing systems poses a challenge for new AI hardware. Future AI accelerators may focus on energy efficiency to reduce operational costs. Collaborations between companies could lead to breakthroughs in AI hardware design. Open-source contributions can accelerate AI hardware development and innovation. AI accelerators are expected to become more accessible with time. The future holds exciting potential for AI accelerators in various industries. Tesla utilizes NPUs to enhance the performance of its self-driving technology. These NPUs allow for faster processing of real-time driving data. Google's AI services are powered by TPUs, optimizing machine learning tasks. TPUs significantly enhance the efficiency of Google's AI computations. Microsoft uses FPGAs in Azure for customizable cloud computing solutions. FPGAs allow Azure to offer scalable and flexible cloud services. These technologies improve performance and scalability in real-world applications. Tesla's autopilot system benefits from the speed of NPUs. Google's TPUs handle vast amounts of data with ease. Azure's FPGAs support diverse workloads with high efficiency. These advancements lead to significant cost savings for companies. The integration of these technologies is a game changer in the industry. For most AI workloads, TPUs provide the best performance and cost balance. TPUs excel in cloud environments with high teraflops per dollar. Their energy efficiency further adds to the cost effectiveness in AI workloads. Leveraging TPUs is the optimal strategy for AI tasks in the cloud.